All right, here's the final lecture on electrochemistry. I know I've broken it up to four parts, unlike the other chapters. But the first part is kind of a tutorial on how to balance oxidation reduction reactions, and students a lot of times have a hard time doing that. I usually spend an entire class period teaching that section. But okay, so this one we're still dealing with electrochemistry, and one of the applications we have of electrochemistry is the electrolysis of water. So you can take water, you can crack it into hydrogen and oxygen. And one of the biggest applications for this is in nuclear submarines. This is how sailors can breathe underwater. They use the electricity from their nuclear power generator to crack water into hydrogen and oxygen. They dump the hydrogen into the ocean, and then they breathe the oxygen. And that's how they stay alive. And they scrub out the CO2 using some amines. So there's a kind of a fishy amine smell that comes from the sailors, and it's from the CO2 scrubber. Because if the levels of CO2 get too high, you can get intoxicated from the carbon dioxide. So we typically don't use this to generate hydrogen. This is typically how we generate hydrogen. We use steam reformation of methane, so either to make hydrogen and carbon dioxide or hydrogen and carbon monoxide, depending on what your desired product is. We can also get it from reformation of hydrocarbons from what do you call it, oil refineries. So this is typically not how we get hydrogen. One of the thoughts was, because we talked about this before, wind energy is pretty much not useful at all. So maybe if you took wind energy and used it to generate hydrogen gas, then the hydrogen gas, you can use that to burn or use it as a fuel source. But the problem with this is, so water, 18 grams per mole, and hydrogen's 2 grams per mole. So 1/9 of the mass of the water is hydrogen. So it's not a very efficient process in terms of mass. So you don't get that much hydrogen from cracking water because it's only 1/9 the mass of water. Of course, 8/9 the mass is oxygen. You generate lots of oxygen. So good thing, bad thing. But like I said, the main use for that is in nuclear subs. What else can we use electrochemistry for is for plating things. So you can put noble metals on things. You can put the metal that you want in a solution of the metal, and you can put the item that you want to have plated in there, and you can run the current through it. It's typically not a battery, right? It's usually actually direct current. Well, alternating current change to direct current. And we plate lots of things. Like we do this for cars. When for bumpers, for the shiny chrome bumpers, what you do is actually you coat a pretty thick layer of nickel on the metal first, and then you coat it with chromium on top of that to get the shiny chrome look. And the chrome level layer is actually pretty small. The nickel layer is much thicker, but we found that out. But we can also plate things. You can plate silverware, for instance, with silver. And that's originally what silverware was. It was made from silver. You can also plate other metals like gold onto things with this process. And if you ever buy cheap earrings or cheap rings that are gold plated, you can always find a little spot where they put it on things. And also, interestingly enough, this is old technology as well. Some of the material, if you wonder, like, what do they do when they put it in the solution? One of the things they use is wood. So you have wooden struts. You can use plastic, but some of them use wood. Because if you use something made of metal, you will plate the metal, and then you're losing product that way. So they use good old-fashioned wood when they mount these things, interestingly enough. So let's do a example problem with this. So gold can be plated out with a solution of containing gold, and the half reaction, gold plus 3 electrons, makes gold metal. What mass of gold in grams is plated by a 25-minute flow of 5.5 amps of current? So let's do this. So this is good old dimensional analysis. You have 5.5, an amp is a coulomb per second, and then you have 25 minutes, and there are 60 seconds in a minute. And notice where we're going here, the minutes cancel and the seconds cancel. So right, if you're following the units, the minutes cancel and the seconds cancel. So then the next thing we need to do, we look at moles of electrons. Moles of electron by Faraday's constant, 96,485 coulombs. So that's Faraday's constant. And now there is 1 mole gold to every 3 moles electrons, and that is from the 3-to-1 ratio of this balanced chemical equation. And then the next thing is the atomic mass of gold, 196.97 grams gold per mole gold. And yeah, there's everything sorted out. So moles of electrons cancel, coulombs cancel, moles gold cancel, and you're left with 5.6 grams of gold. So go ahead and calculate out all the stuff there. So, okay, I'm looking at the textbook now. I guess they started with time. The way the textbook's probably a better way to do it. It had 25 minutes times 60 seconds per minute times 5.5 coulombs per second. So that way. Okay, but same thing. All right, so this is just plain old dimensional analysis, and make sure you have the proper. The part that students have the hardest time is actually right here, getting the stoichiometric ratio. Okay, and other applications, we can use electrochemistry to make bleach. And this is important. Bleach is fairly important because we use it for water purification. Well, I should say chlorine gas. So making chlorine gas, we use it for water purification, things like swimming pools and in municipal water supplies. Here in Maui, we do chlorinate our water. On Oahu, they typically don't, unless there's unless they can find the. They test it for microbes. If there's enough pathogens in the water, then they do go ahead and chlorinate it. They don't test for chlorinate, but they don't test for pathogens in the mouth. They just go ahead straight and chlorinate the water. That's one way they get around that. But yeah, you can use this way. So you can use a sodium chloride solution and put it in anode and cathode, and you can generate chlorine gas and hydrogen gas. And then the chlorine gas, if you bubble it through, you can make so the this is one way. Well, it'll form sodium. Well, it forms sodium metal too, but then the sodium metal forms hydrogen gas. And among other things, you can tweak this to also make bleach. So making bleach, making chlorine. The way they used to make chlorine is that you would have to take salt and you'd melt it. It takes a lot of energy to melt salt, and then you would use electricity, like the same old thing, reduction of that using something like carbon, and or you can melt it and you can do electrolysis. I guess electrolysis is a popular way to do it, and but that takes a lot of energy. So using the aqueous solution is better. And the last thing, well, it's application corrosion. Corrosion is a big thing with metals, and corrosion is a multi-billion-dollar, billion with a B, dollar problem. And we're very familiar with iron. Iron rusts. When iron corrodes, it forms rust, which is an ugly brown color. But more importantly, rust is not very sturdy. So other metals, so titanium and aluminum, for instance, they are much more reactive than iron. But the difference between iron and titanium and aluminum is that the oxide layer that titanium and aluminum forms, it's very tough. So aluminum, actually, the oxide layer is called sapphire. Aluminum oxide is the second hardest naturally occurring mineral. So, but aluminum or titanium also is very tough on the surface. And actually, with titanium, the oxide layer is what gives titanium its rigidity. So titanium without that oxide layer is very soft. So we know titanium to be a very tough metal, but it's really, I mean, without that oxide layer, it's not very tough at all. But iron, unfortunately, forms an oxide layer that's really soft and flakes off. You could flick it off with your fingernail if you wanted to. And we make so many things out of iron, this is a problem. And it forms via a electrochemical reaction. So the iron metal is the anode, and the rust itself is the cathode. And what happens is dissolved oxygen reacts with the iron, and it forms iron oxide. So iron oxide rust, typically iron 3 oxide. And so we want to prevent corrosion. How do you prevent corrosion? Good old drain the swamp, as they say. Keep it dry. So you might notice that wet iron oxidizes more quickly. So if you keep it dry, it's not going to oxidize as quickly. Another one is to have something called a sacrificial anode. So sacrificial anode is a cheaper metal that's more active than iron. So typically zinc is used. So you can coat the iron in zinc. That's what galvanized means. So galvanized iron is iron coated in zinc. So the zinc oxidizes first, and when the zinc's gone, then the iron starts to rust. But what you can do, though, let's say you have a pipeline. So if you're wondering what the difference between a pipe and a tube, tubes are extruded, pipes are welded. So pipeline is a sheet of iron. You weld it in a just around, and then these are iron. They will corrode. So how do you prevent the iron pipeline that you spent so much time and effort putting in? Well, when you put it in, you attach slugs of zinc. So you take a wire, a big slug of zinc, and then you stick that on there, and you connect it up to the iron. And then every 5 or 10 years, you go through and you replace that big slug of zinc. So that's some people's jobs, is to go around, dig up, find out where these slugs of zinc are, dig them up, and replace them. So that's the sacrificial anode, and that's also how galvanized steel works. The last part is passivity, and some metals do this naturally. So I mentioned aluminum and titanium; they naturally pacify in the presence of oxygen and form the really thick oxide layer. And the passivity. So if you do this with iron, if you throw iron into nitric acid, it'll bubble up. It'll be very exciting reaction, and then it'll slow down, and then slow down, and then it'll stop. It'll form this thick passivated layer, and this thick passivated layer prevents ions from getting in, and so that's why it's called pacified. It's a passivity. It's a pacified layer. Unfortunately for iron, the oxide is not very strong, so it's pretty easy to get through that oxide layer. They've done this with some buildings. This was popular in the 1970s. They would pacify some iron by using nitric acid, and you can see kind of some brown, ugly buildings made this way. But it's not as common anymore. We typically use more sacrificial anodes, is probably, and also keeping things dry is used more frequently than passivity for iron, although it can be done. The other thing about passivated layers, so they can be penetrated by certain things. I mentioned titanium. Titanium can be, this passivated layer can be penetrated by methanol. Methanol gets right through that layer, and titanium and methanol do not mix. The methanol causes the titanium to rust very quickly, or corrodes very quickly. Same thing with aluminum and chloride. So if you wonder why don't we have aluminum pipes? Why don't we have aluminum boats? You can have aluminum boats in fresh water. So if you notice something as an aluminum boat is always in fresh water, you don't typically see aluminum boats in the ocean. And why don't you? Because the chloride anion can penetrate through that passivated layer and then starts to corrode the aluminum. If you want, you can take some aluminum foil and stick it in salt water, and that salt water will corrode. Well, the chloride will penetrate through and it'll corrode the sapphire. It'll turn it all into aluminum oxide, so it'll turn into sapphire. So the aluminum will turn into sapphire. So if you want to make your own sapphire, go ahead and take aluminum foil and stick it into salt water, and you'll get yourself a bunch of sapphire. Of course, sapphire is just white powder aluminum oxide, so it's not that exciting. It's not the crystallized like the gemstone sapphires. If you want to know sapphire gemstones, iron, titanium impurities are what gives it a blue color. If you get different colored sapphires, different metal impurities give the colors. So chromium impurities causes sapphire turn red, and red sapphires are usually also called rubies. So you get different colors. Different colors mean different things, different impurities. Sapphire, pure sapphire, is actually kind of a smoky, clear color, so not that exciting. But you can grow them in a lab very easily. Okay, so that is the electrochemistry. So next topic is coming to the end is nuclear chemistry.